Hello, everybody. Thanks for coming to my talk, Analyzing, Visualizing, and Improving Wikidata using the Wolfram language. Thanks for having me here at the Wikidata Conference 2021. My name is Toni Schindler. That's me in this picture here. And I work at Wolfram Research. At Wolfram, I work on ontologies, or better, the framework. I work on semantic web technologies, and I implemented some functionality for accessing Wikidata. In my free time, I also edit Wikidata. So I've been with Wikidata since the beginning, and I've been editing actively for a little bit more than 3 years now. I mostly edit manually, but as every other human, I do mistakes. And when I find them, I try to do some analysis to find other mistakes of this kind. So I got some experience doing that, and that's why I volunteered doing this talk today. So let's see what we are talking about today. So just a quick check. Oh, sorry. Right. I'll give a quick 35-minute presentation, and after that we can have a discussion. Otherwise, it might be too difficult for me to pay attention to the chat while also presenting. So I'll have a look at the clock. So a theme through this conference has been data quality, and I hope I can contribute something to that discussion. We are going to use the Wolfram language. Some of the things I'm showing, or many of them, can be done in other programming languages or without any programming language, just using the Wikidata query service. But other things are pretty convenient in the Wolfram language, and I'm going to show that today. In order to get to data quality, we have to do some basic, or we have to learn some basic things. So we'll start with a quick introduction to the Wolfram language. Then we'll focus on knowledge representation, maybe the most important aspect for Wikidata. Then we'll look at retrieving and querying knowledge. Then, in order to learn some of those concepts, we'll do some visualization. Then we'll look at one aspect of the Wikidata ontology, namely quantities and units, which is where I know something about. And we might touch a little bit on Sparkle and Wikibase. But don't worry, you don't need to know any of that to follow the talk and learn something new. So, what is the Wolfram language? The Wolfram language is a programming language with a lot of built-in functionality. For instance, you can do symbolic computation, like taking the derivative of the sine function, which is cosine. You can do visualization, and of course you can do programming, as we can see below here. This is a 3D plot, so you can actually turn it around. So by the way, this sign is called a symbol, also D is called a symbol, and the Wolfram language contains nearly 6,000 built-in symbols, just to give you an idea of the size of this programming language. So those are from different areas of computation. So let's focus on one area of functionality, knowledge representation. The Wolfram language has a built-in knowledge base. In order to refer to something, in order to ask questions about something, you need to be able to refer to it. And to refer to something in the Wolfram knowledge base, we use entities. Here you see an entity in this nice yellow-orange box. And as the tooltip shows, I hope you can see the tooltip. An entity consists of an entity type and a name. The entity type determines what the available properties are for an entity. And a moon has as property, for instance, distance from Earth. And if I evaluate these expressions, it's getting the latest data from the Wolfram servers. So as you can imagine, the distance from Earth is changing all the time. Complementary to entities, we have external identifiers. External in the sense of external to the Wolfram knowledge base. And we use them to represent other identifiers. In this case, we represent the Wikidata identifier Q1. And as you all know, this refers to the universe. But if you don't know, we have the possibility to include arbitrary meta information into an external identifier to help humans, for instance, recognize those identifiers. Yeah? So if you can embed arbitrarily meta information, if a label is presented, this is used for typesetting. And what can you do with those external identifiers? Well, there's a growing number of services that understand external identifiers, and the first one of them is a set of Wikidata functions. Those functions come in pairs. Typically, there's a search function which allows you to discover identifiers corresponding a bit to the search box on the Wikidata website. Here I was looking for the play by Goethe, Faust. And as the description shows, yes, the first one was the correct one. I can copy and paste that. I can also look for properties and then stuff it into the corresponding data function. And when I evaluate that one, it contacts directly the Wikidata service for retrieving that information. And you can see that we natively support dates. Just one of many data types that we support that map from Wikidata to the Wolfram language. So far we have seen retrieving data for one entity or one item, but we want to get to queries. But an intermediate step would be to ask, well, what do we do if we have multiple items? In this case, let's look for the median income for 3 countries. Wikidata takes a list of items and retrieves the value for each item. Here I can choose a result format, in this case an association, which is the Wolfram language way of representing key value pairs. So this is helpful for associating the result with the input where it was coming from. And note also the result for each input is a list. This is just because Wikidata places no restrictions on the number of statements that there can be on a given property. So it can be no value, one value or more. So for consistency, it's always going to be a list, and it's up to you to decide what to do with it. So now that we've seen a single item, a list of items, now let's go to queries. In the Wolfram language, one way to represent queries is using entity classes. Class in the sense of a collection. And here we represent the class of all elements in the sense of chemical elements with an atomic number less than 5. In this case, this is a predicate that returns true or false depending on whether the atomic number for a given element is less than 5. And what can we do with this entity class? For instance, we can look up the value of a property for all of its members. In this case, the atomic symbol. And the same mechanism can be used in the Wikidata function to query Wikidata. In this case, we are looking for telescopes whose focal length is amongst the largest 5. And we can use this entity class in place of a list of entities and request, for instance, the countries in which they are located. And just to show a different way to format the data. Here I'm requesting a data set. Just checking whether there are many messages. Hello, thanks. So, okay. As we can see, here we got the largest telescopes, and I chose this example just to, because I found very interesting the names they're giving to them. Great, extremely large, and overwhelmingly large, and so on. So this does not have a country because it's planned to be constructed, I guess. And now that we have covered the basics, oh, by the way, remember, you haven't seen any Sparkle or Turtle or JSON or any other scarily sounding technical stuff. And you can already do queries and request data from Wikidata. So this is maybe one of the powerful features of the Wikidata function. In a very user-friendly way, you can write already queries. And now let's get used to this way of querying Wikidata by doing some visualizations. And let's focus on movies, for instance. Remember entity classes? We are looking for movies that have a duration specified in Wikidata, of genre science fiction. And we want all of the durations. And then maybe one of the arguably simplest way of visualizing them is using a histogram. Yeah. So what is a histogram? A histogram creates a few bins, yeah, and counts how many values are in that bin. Yeah, and in this case, we see that between 1.5 and 2 hours. Yeah, note the unit nicely displayed on the axis. Yeah, there are 25 movies. Yeah, so this seems to give a tendency of how long sci-fi movies are. Yeah, but more interesting would be to compare the length distribution across different genres. Yeah, so we take the same query as before, but this time we request the data for 3 different genres. Yeah, and we can immediately visualize this list of results. Yeah, and in this case, we see that apparently the political thrillers seem to be longer than drama and sci-fi movies. Yeah. Now, staying with movies for another moment. Yeah. Let's get all the movies starring Quentin Tarantino and take the latest by publication date, or the largest. Yeah. So here are a few movies, and what can we do with them? We can make, for instance, a timeline plot. Yeah. So this is a very nice visualization of the result. We can also do visualize time intervals, but yeah, there's just so much time. I want to get to some interesting topics. Yeah. So let's stay again with movies for a moment. In order to get a diagram where there's a quantity on 2 different axes, we need to compare. We need to retrieve different values. So yeah. Let's start with a class of all movies. Yeah, whose language is, or whose original language is German. And for all of those movies, let's get a publication date and the duration. Yeah, and let's clean up this data a little bit. Yeah, so typically there are multiple dates stated. Yeah, different release dates. We want the minimum of those. Yeah, and the duration is a list. Remember, everything is a list, and we just take that duration and make a time series out of it. And given a time series, we can easily visualize, yeah, how the length of German language movies changed over time starting 1900. Yeah. So, however, this looks a little bit coarse, yeah, and of course we can compute, given a time series, the moving average, and then overlay the 2 time series in one diagram. Yeah, and you can see this little gray bubble here. I can specify a lot of visualization options, yeah, that I'm hiding here, so you can focus on the contents. Yeah, so here I'm taking the moving average with a window of 5 years. Let me check the time. Okay. Another way to visualize things is geographic visualization. You can also do that using the Sparkle endpoint, for instance. But the important aspect is let's restrict. The important aspect is the simplicity with which you can query using entity classes. Yeah. So far, you have seen that an entity class takes a rule or a list of rules. Yeah. But I can also specify a geodisk. This is maybe self-explanatory. The disk is centered in Barcelona, and I'm taking a radius of 10 kilometers, and I want movie theaters. Yeah. And I'm just taking all of the positions. Yeah. And I'm making a nice plot. However, we might not only want to visualize the positions of certain things, but we want to plot values, yeah, corresponding to those positions. Yeah, and one example is we are interested in coal-fired power stations centered again in Barcelona, taking a radius of 1,000 kilometers this time, and we want the position and the capacity. Yeah, so that means the power output of that power plant. Yeah, and some of them are going to be missing the position, other the capacity, but I'm going to take all of the pairs, yeah, and transform them into a rule. Yeah. And one of my favorite functions from the Wolfram language is the random sample, which quickly lets me peek into the temporary result to see whether I'm doing these things right. Yeah. And I can just stuff this list of capacities, this cleaned up list of capacities, into a geohistogram. Yeah, and we can see here visualized as clouds where many of those power plants are. Yeah, so yeah, interesting. Yeah, But I can also visualize, for instance, the individual power plants, yeah, using the same original data, where each power plant receives a bubble corresponding, whose size corresponds to power output. Yeah? However, those visualizations have some shortcomings. Yeah, so there are very few end dates specified, and maybe the efficiency might also be interesting, and maybe other properties to really get an idea of, well, how healthy is it actually to live in a certain region? Yeah. So, talking about healthy, let's talk about life expectancy. Yeah. Let's get 3 random countries, yeah, and ask Wikidata about their life expectancy. Yeah. So the Wikidata function is respecting the ranks, and by default is returning the best ranked values for given statement. Yeah? And in this case, we are presumably getting the last non-deprecated statement. Yeah? However, we are interested in time series for each of those countries. Yeah? So if you don't like code, let's simply look away for a moment. So we have here some experimental methods for specifying that we want non-deprecated statements. That means including normal and preferred ranked statements. And we want, instead of just the value, we want an association of all the data relevant for a statement. Yeah, and this is how it looks like for each country and date. Yeah, we get the value as originally, but also the qualifiers and references and so on. Yeah, and then we can do a little transformation that as homework you can figure out how that works. Yeah? And we get for each country a time series, and we can immediately stuff them into our date list plot, and we can see that all of those curves are going up. Yeah? Quickly checking whether there are any chats. Okay. So, taking any of those time series, we can do some extrapolation. Yeah. So there are a lot of analysis we can do on time series. Just one example is we are fitting a model and we are not specifying anything, so it's taking some defaults. Yeah. And we can extrapolate how in 10 steps, that means 10 years in this case, the life expectancy is going to go up. Yeah. In this case, the latest value is a little bit outdated, so we could compare this curve actually with some actual data. Yeah. So just some fun. I would have liked to come to Brazil for this conference, or wherever it would have been. Yes, but yeah, let's get some image URLs for beaches centered on Brazil within a radius of 1,000 kilometers, and take up to 10 random URLs and make an image collage out of them. Yeah. Just so we can think about beaches for a moment. Yeah. So far we've been talking about numeric or data, yeah, but a large part of any knowledge graph is relations between entities, and a subset of those relations can be visualized or represented, more importantly, as a tree. And here's a random tree. It has a root and some children, and those children can be the source of another tree. Yeah, so 10 is the source of another tree of 7 and 1, and so on. Yeah. So now we can build a tree using data from Wikidata. Yeah. So this one is not the most efficient way of doing that, but it's a very instructive one. We have a function called nest tree, which takes a function that, when fed an expression, is supposed to return a list. Yeah. And you know, for each input there might be 0 or more children. Yeah. And we start with the queen and we nest 2 times. Yeah. So there we can see below the queen there are the children and the children of the children. Yeah. So, however, not every data fits into trees. The most general thing is a graph. Yeah. And here's a random graph. And the way to construct one is the same. Let me check the time. Okay. Oh, I'm running late already. Nest graph works the same. It takes a function that is producing a list. Yeah, here the subclass of relation is taking something and returning the elements, which it is a subclass of. Yeah, and we start with human. Yeah, and we nest 6 times this time just to see how we are going to reach entity, our top concept. Yeah, And this way of visualizing is very important for finding mistakes in the data model. Yeah, and see, yeah, okay. So one thing that struck me is, okay, a human seems to be an omnivore, yeah, and an omnivore is a consumer, and that one looks weird to me, but when I read the description, I said, okay, consumer in the sense of, yeah, species, science. So this whole graph seems to be pretty okay, yeah. So note that graph layout is a very hard problem, but we are trying by default to give you a very nice layout, but you can specify with options different graph layouts. Yeah. So again, I'm hiding them here to not show you any unnecessary code. So now that we are familiar, let's look for a moment, or let's step back for a moment and look at data types. Yeah. So what are data types in Wikidata? Yeah, so data types are the kind of data that a property supports. For instance, external ID means that a property takes, well, external ID values, and quantity means that the property value will be a number or a number in the unit. Yeah, so here in this visualization, the data types receive the size depending on how often they are used as properties, and we see that quantity is fairly important. Yeah. Maybe after external ID and Wikibase item. Yet it is a very tricky data type to get right, not just in Wikidata, but in any programming language, because it requires some actual curated data. So that's what I wanted to focus on for a moment. Yeah. So what is a quantity? Well, a quantity is a number and a unit. And the Wolfram language fully supports quantities. Quantities have some basic information like the dimension, yeah, like 7 meters, or yeah, has a length dimension, and you can convert quantities to other units. For instance, 7 meters are 7,000 millimeters. You have seen already quantities used in visualization functions where unit conversions are automatically considered. Yeah, but just to show how it works underneath. Yeah, so adding 2 kilometers to 800 meters, yeah, automatically chooses one target unit and does the addition correctly. And even so, 2 is smaller than 8. 2 kilometers is indeed greater than 800 meters. Yeah. And corresponding to a quantity are quantity variables, which are basically symbols where a physical quantity has been attached. Yeah, so there's a nice tooltip. This A represents area. And those also have basic data. For instance, an area quantity has a typical unit of square meters and length squared. Yeah, and units, quantity variables are used in the Wolfram language in formulas. For instance, here the Stanton number, some characteristic number expressed in terms of quantity variables. So this is a fully semantic representation, which Wikidata still has to work on a little bit. I would guess Wikidata is there 30%, and we can discuss that later, why I say that. So how are units useful in Wikidata and elsewhere? Yeah. So whenever you enter a quantity valued statement, like the mass of something has such and such number of unit, yeah, then this unit actually is a Wikidata item. Yeah. So this item has properties like the quantity it expresses and the conversion to an SI unit. So here's just a very quick overview of the ontology that I'm not going to show in detail, but just to point out how difficult the whole ontology is. Yeah? So units links to various ontologies, including the Wolfram language, but also others. QUDT, originally from NASA, and UN unit ontology. Yeah. While units also link to measured quantities, and quantities link back via recommended units of measurement, yeah, because there are certain outdated units that are not recommended anymore. Quantities also link to certain ontologies. Quantities have symbols, units have symbols, properties have unit classes, quantities are linked to properties, and so on. Yeah, and here's just an example of that. Yeah, so millimeter expresses length, and the recommended unit of length is meter. Yeah, and millimeter has a conversion to an SI unit, but also conversion to some other standard or less standard units. So how do we ensure the quality of all of those relations? Yeah. Before getting there, let's look at alignment. Yeah, alignment has been mentioned in some talks before, so let's look at alignment of units. For all the units, that means an entity class of units. In this case, I'm not specifying any condition. That means give me all the units of measurements. I want, well, first of all of the links to external ontologies, or at least a selection made by me, maybe the 5 most important ones at the moment. Yeah. So we see that there are 7,200 unit items in Wikidata. However, we see that only 2,200 of them are linked to at least one external ontology. Yeah? So there are about 500 items that are linked to all 5 of those ontologies. Yeah? So those are the very important unit items in Wikidata, and thereby probably also highest quality by now. So here we can quickly count how many Wikidata items are linked to each ontology. We can see the Wolfram Language unit code is winning here, and then is coming the UCRM code. But those are special in a way that, given a few basic identifiers using algebraic combinations, you can form arbitrary number, while the others have a curated identifier, just like Wikidata. So this comparison is not quite fair, but nevertheless useful. So the same goes for quantities. We have quantities aligned to 2 quantity ontologies, the Wolfram Language and QUTT again. Yeah, and here just a random selection of quantity names. Yeah, 30 quantity names from the 500 or so important quantities. Yeah. Just to get an idea of what we mean by quantity. So, what do we do about the quality? Finally, I can get there. Let's see whether oh, no. Good. So let's retrieve for the unit millimeter, that's a special property that expresses that in a Wolfram Language quantity, and the conversion to an SI unit. Yeah, and note how I use the structuring here to result in a unit and a converted variable. Yeah. So that means now unit is 1 millimeter and converted is, according to Wikidata, 0.001 meters. And I can use the Wolfram Language to verify that those are the same. Ah, yeah. And here we see this gives us an opportunity to do some conversion checks. And oh, forgive me, now we really see some code, but if you don't like code, don't worry, just look away. But I'll explain a moment what we do. So the first important thing is to check that the Wolfram Language unit code, which is some actual code, is correct, and it's correct for all. We do that by retrieving them. And then we are checking whether the single value, yeah, it needs to be a single value, whether it's actually, well, one is an exception or a real quantity. Yeah, and we get just 2 failures. This is because users can enter actual real Wolfram Language code, and we needed to be sure that no malicious or funny person entered some code that, for instance, quit your session or worse. Yeah, so we were overly strict in validating the code. This has been fixed in the upcoming version 13 of the Wolfram Language. Yeah. So now that we verified that all of the codes are correct, yeah, let's compare some of the conversion factors. While in DSI and some modern units, the conversions are exact or pretty well known. When we go to more historic units, we need to be a little bit less precise. So that's why I introduce a function here, pretty close, which still returns true if within a certain tolerance the results are pretty equal. Yeah, and then we can compare all of those unit conversions, and we see that there are 1,800 applicable unit conversions, and most of them are correct. Yeah, just a few of them show some issues, and yeah, I have been having an eye on that list for 3 years now, and it's shrinking slowly but carefully. Yeah, so doing such kind of checks, I identified errors in basically every ontology, and I contacted various of them, and they're always happy to receive those corrections, yeah, or those hints. Yeah, we can do the same for quantity checks. Yeah, here's just a little thing that I'm not explaining due to time limitations. Yeah, but just one point. Queries I entered in the Wikidata query service with the help of autocompletion. I can store in the notebook and then reevaluate them. Yeah. Here we are doing some comparison, comparing the Wolfram language unit to the Wolfram language quantity dimensions, and we can see that we have no issues so far, but this was a lot of work to get there. So no time to explain that in detail. So just an overview of what that actually did. So the technically inclined might know that in order to do queries like give me the largest or the heaviest and so on, the Wikidata query service needs a way to compare quantity valued statements. And for that, it needs to be able to convert quantities given in any unit to a common unit. And those conversions are generated from code which is derived from Wikidata. And we got the latest update of this code just at the beginning of this year, and there were some actual fixes, thanks of the fixes in Wikidata, thanks of those automatic conversion checks. And there was a 2008 unit ontology review. Here we can see the number of quantities and units they were comparing. So they were a little bit smaller by them, but they also faced a lot of issues because they had to manually align many of the ontologies. We now have those alignments and the quality is much higher. So I would really encourage someone to redo such an evaluation, but building on the much higher quality and the alignment that we have now. I'm actually in time. So sometimes the watch list is not enough because you might want to go on vacation and not see anything for a week and then not have to worry that you miss things. So what I'm doing in this case is I'm generating an association of all Wikidata items that have a certain alignment. In this case, that's something I'm currently curating. And I'm storing that in a variable, the result, and I'm iconizing it here. This is our way of storing things in a notebook. You see here the number of alignments. From the previous run, I have all of the alignments that were current at that time, and here I'm comparing them. Homework, figure out what this little code is doing, and I'm seeing that, so one is, and I'm seeing the difference from the previous time, and I can review, are they all okay? And then I just, if I'm fine, then I'm stuffing that into here and save my notebook. And in this way, I'm not having to worry that I'm missing accidentally something from at the watch list. Here's just a complementary way of doing it. We can load packages into the Wolfram language. Here is a little package that I used to generate unit labels in different languages from UCOM code. Here's an example that shows how I convert the code into an English label, kilometer per second, or the same code into a Spanish label, kilómetro por segundo. And then I can verify whether such a generated label is already amongst any of the label or the alternate labels. And doing that, I can generate a list of possible cases to look at. And it seems pretty good. And the great thing is I have done this analysis already for a year now. And we see that the English labels could be verified for more than 1,100 unit items. And similar numbers for certain other languages. And I actually contributed some of those labels once I was confident that the transformation rules are correct. And here I'm visualizing the unit items and the language depending on how many unit labels they have. And you can see that German, English, French, Spanish, and Hungarian stick out somewhat, which is exactly the units where I have improved the labels using those automatic checks. Oh, we are nearly at the time limit. By the way, talking about languages, the Wikidata functions support a language option. And actually, if you're using the Wolfram language, and you configure the user interface to a specific language, this is automatically respected. Here I'm looking for hard in Spanish labels, and that, yeah. And setting this option also embeds in its meta information everything in Spanish, yeah. And also the data that's coming back from the Wikidata data function is all in Spanish. Note, for instance, the labels and descriptions of the properties. Yeah. And this is my second last slide. You have already seen one Sparkle query. Yeah, so the Wolfram language has built-in support for semantic web technologies. Yeah, so for instance, querying a Sparkle endpoint. Let me quickly check. No new messages. Great. In order to query a Sparkle endpoint, you need the URL to that endpoint and the Sparkle query. And Sparkle execute will do everything it needs to do to ask the question to this endpoint and interpret the result. In this case, interpreting the date value and converting it to our built-in date representation. However, there's a more difficult way of doing that. I'll explain in a moment why you would want to do that. We have a symbolic language for representing Sparkle, and note all of Sparkle 1.1. And here I'm just representing a triple pattern, and I'm constructing the subject, the predicate, and the object, and I'm choosing a query form, and the result is the same. And why would someone do that? Well, if you're just copy and pasting a query from the query service into your notebook, that's fine. But if you're writing any application and the Wikidata function is a large application, then joining strings and handling all of the data conversions from our built-in representation to Sparkle is so complicated and error-prone that it's better to use the symbolic representation. So just to give you a little fun fact, the Wikidata function has about 10 source files just dealing with composing a single Sparkle query for all possible inputs, dealing with different data types, different ways to input your request, and so on. So this is the first actual user of the symbolic representation of Sparkle. And my last point is, so can you use the Wikidata function just for Wikidata? Yes. However, we built below Wikidata a function called some Wikibase functionality. And this is not documented, and let us know if we should do that or how much you're interested in that. So how would that work? You specify a Wikibase configuration where you give some basic information like what the concept type would be, what a concept base URI would be. And here I'm just using Wikidata again. And then you have a function called Wikibase search and Wikibase data, and they just work the same as the built-in Wikidata functions, but they take your configuration and then they just work like the built-in function. So that means using those not documented features, you can actually connect to your own Wikibase installation using the same powerful feature that the Wolfram language connects to Wikidata. So, and this is the end of my official talk. And just one comment, I generated this little cloud using Wikidata items and labels. I tried to use lexemes, but this was a little bit sparse, so please help filling out the lexemes related to that. Thanks, everybody. Now I can maybe listen to some questions or pay attention to questions. Are there any questions? So Aaron is mentioning that he would like to hear more about the Wikibase function. Yes. So I can't announce anything yet about this function, but just that I'm equally excited about this function, and I would like to continue developing that, or developing and further see how useful it is. I think that now that there's a Wikibase manifest, which was not available when I started developing the Wikibase functionality, that certain things will be even easier. So you might have to configure even less to connect to a Wikibase installation that supports a Wikibase manifest. Yeah, so that's my comment about it. Yeah, Aaron is asking whether this is documented in Wolfram Language 13. Wikibase, no, but all the other functions I've shown are documented, yes. So TPT is asking about whether we are using the Wikidata query service for entity class queries. So this is a great question. Yeah. So if I'm doing some live coding here. If you do something like this, yeah, where you have an entity class where the first argument is speech, yeah, for instance, then we are using our internal mapping of our objects, that means as entity types, entities, and properties to Wikidata items or corresponding Wikidata properties. Yeah? So this speech is going to be translated to a Wikidata item. Yeah, and from all of this input, a single Sparkle query is constructed that is then sent to the Wikidata query service. Yeah? And then the result is interpreted and put into the structure that you have seen in this talk. Yeah? Yeah? Yeah, so TPT is asking whether we are targeting the Wikimedia instance. Yes, we are. So you get the latest, most up-to-date data. Yeah. Maybe another interesting thing to consider is, yeah, so, or that I would be interested, how much query are we getting at Wikidata from Wolfram Language, from the different versions, and how much is the Wikidata function responsible for it? Also, I would be curious to know how it's coming with the Wikimedia Commons query service and what we can do to connect to that one. There we would probably need some authentication mechanism to connect to that. Yeah, and the Wikidata function is half prepared for that. So there's a not yet documented function for authentication. So if Wikidata would ever require or encourage at least authentication, then we might user might be able to just include some string, so to allow better classification of who is causing traffic. Yeah. By the way, as long as there are no questions, I could maybe show one little backup slide that I have, because I found that very interesting. So if no one objects, so yeah. So the formula graph, yeah. So earlier I mentioned that Wikidata might be there 20 or 30% having semantic formulas. What do I mean by that? Yeah. So let's take an item about a physical quantity and request the defining formula. And we can see that we can visually represent that. However, formulas are entered using LaTeX and then converted to presentation MathML. And that means that by definition, those are not semantic representations. Yeah? So it would be really cool if Wikidata had representation MathML editor to put in actually meaningful formulas. Yeah. However, now let's see. We have a new model for explaining at least the symbols in the formula. Yeah. This property is called, and it has been long used in defining formula, but what it's new is this qualifier symbol represents. That means we can attach to each symbol the actual object that it represents. Yeah? So this is great. However, what I wanted to show is going from each formula, looking at the variables that it contains, we can create a graph that shows the connections between the different quantities. Yeah? And let's see this graph. Yeah, and this is really impressive. Yeah, so this is only the formulas that actually use symbol represents. So this is pretty new. So I've been migrating some of those statements, and I saw this graph growing over time. Yeah, so it's really large, and we can, for instance, see some popular quantities like the area is a pretty important quantity, yeah? Or duration. Yeah. Kinetic energy. Yeah. So this is maybe not really, mass is a very important quantity in science. Yeah. So this is maybe not very educational. However, if someone wanted to put that as a poster into their bedroom to visualize or remember visually, or help them learn certain formulas, let's say in chemistry or physics. Yeah. So this might be just one of the possible ways to do that. So that's the formula graph, or a subgraph of formulas in Wikidata. Any more questions? Otherwise, I have another backup slide. Yes, thanks for the link. I know Physikerwelt was involved in various of the conversations. Yeah. Yes. Thanks for the links, TPT. Okay, let's just look at one more backup slide. So it's going to be the last one. Yeah. So let's please look away. This is just 2 pages of code, but what can we do with this code? We can build a little query builder. Yeah? And let's look at, let's enter a property. Let's hope that works live. Focal length. I had already, yeah, and we want things whose focal length is greater than 50 meters. Yeah, okay, make it so. This is now from this input generating a symbolic representation of your query, and let's evaluate that. Well, and here we get all of the telescopes together with some input values. Yeah, and your homework would be to add more certain things. Yeah, and add support for more data types. Yeah, but this is just to show that we have a little query builder, or we can build a query builder in the Wolfram language. But here's, of course, the real thing that has support for more data types already built in, but maybe not for quantities. So that's from my side. Any more questions? Well, if there are no more questions, then I'll stop sharing my screen. And I think we got a pretty great result when preparing. I had material for more than 2 hours, and it was very hard to bring that down to 35 minutes. Well, thanks everybody for listening, and that's it.